Good to go. Okay, so good afternoon, everyone. So my name is Shi Zhang. Currently, I'm a PhD student in Professor Darren York's group at Rutgers University. So it was supposed to be Darren speaking here, but he got a time conflict, so he sent me here. And today I will be his stunt double. Hopefully, I could make it when I fake it. Hopefully you like me, but if you don't like me, then you actually don't like Darren. Okay, no. So this is the very last talk of the day. So thank you for patience. Now let's begin. My topic is actually about the modern free energy methods, especially designed in the Ember software package. Specifically, my own research focused on the alchemical free energy methods, which is capable of doing a lot of things that by leveraging this artificial alchemical coordinates, that's the lambda parameter, that to change from one end state to the other. Now, the definition of the end state is quite arbitrary. It can be kind of two different ligands. It could be the one ligand but with different binding mode. It could be the one ligand with different protonation states. Now, in this transformation process, a lot of thermodynamic properties can be calculated. Now, within our context, the protein ligand binding affinity will be the most important thing for drug discovery. So there has been kind of quite a lot of effort trying to introducing reliable and robust free energy methods, especially into the Ember drug discovery, the kind of package. These are kind of several excellent papers recently describing the advancement within Ember. And now Ember has quite a lot of integrated all the advantage free energy methods, and all of them already run on the GPU side. So it's probably one of the fastest code that is available, but still at a price. So recently, Darren has this kind of review paper on the modern alchemical free energy methods for drug discovery. So pretending it's my paper, okay? And in this paper, Darren there are several discussion about various aspects, such as which method you should use for your free energy, whether it's equilibrium sampling or non-equilibrium work, the methods, and what kind of criteria should we look for when we actually analyze our free energy simulations. And also there are discussion about the different tiers of complexity in the binding affinity calculations. Now, if we start from the easiest case, that is, of course, when your compounds share a common molecular scaffold, and in the same binding site, they have the same binding mode, but they only differ in one or two R group with different fragments. In this case, you will just calculate using the RBFE with the alchemical enhanced sampling method, that is the ACES, which is developed within our group, and I will talk about it in the next slides. So the second tier is that when your compounds have different molecular scaffold, but luckily they are in the same binding site, and even more luckily if they share some similar binding mode. Now in this case, you will just run this core hopping binding free energy, which is the CBFE, which is composed of two counterpoised ABFE calculations with the ACES method. And at the same time, probably you need to introduce some lambda-dependent restraints. For example, the lambda-dependent Borel restraint to hold the ligand inside the binding pocket when you kind of completely turn it off into the dummy states. Now, the worst scenario is that when your compounds have significantly different binding size or binding modes. In this case, you need to run these ABFE calculations with the lambda-dependent restraints. If you happen to have quite a large network, a large ligand library, you want to run ABFE on all of them, probably you need an end-state reservoirs for the apo structure of your apo structure of your protein. Why is that? So imagine that you are turning off your ligand inside the binding pocket, and when you turn off all the interactions between the ligand and the protein, the binding site will likely undergo significant or drastic conformational changes. And when in its apo structure, it could have slightly different conformations or structures starting from different ligands. Now, in this case, to improve your systematic precision, you want to force the end state of the Apple structure to be the same ensemble. In this case, you can use end state reservoirs in your simulations. Now, I will talk about this alchemical enhancer sampling method, the ACES, within our group. It has the kind of several features. The first is the usage of the smooth step, the latest smooth step soft core potentials to connect the two end states. So this soft core potential is designed to transform your van der Waals and electrostatic interactions in a one-step concerted way, so instead of the kind of the decharge van der Waals charge, the three-step way. So we have tested against kind of several systems, a neutral ligand, a point charge, and a kind of a charge-preserved transformations. And they all kind of produce a very smooth DUT lambda profile along this kind of lambda coordinates. The second feature is that the usage of the Hamiltonian replica exchange for efficient counter diffusion of the real state and your enhanced sampling state, that's the dummy state. So when your replicas or when your system has a higher Hamiltonian, it will be easier to kind of overcome any energy barriers. And when you have kind of the replica exchange, it will help to kind of tunnel through this any kind of energy barriers and help to for the enhanced sampling purpose. Now, these are the advantage of the ACES method. It enables the seamless integration with free energy simulations, and the more efficient kind of enhanced sampling allows ACES to overcome some local hotspot problems if you select the correct enhanced sampling regions. So this and the enhanced sampling region can be also it is very flexible. So for your traditional RBFE calculations, you will select the common scaffold into the common core region, which it does not change during the alchemical transformation, and you put that different R group of fragments into the soft core regions. And if you try to run the CBFE calculation, that would be even easier. You just select the whole ligand into the dummy states, into the soft core region, sorry. And if you happen to like want to sample the protein side chains and the interactions between the ligand and the protein side chains, now you can just include the protein side chains in the ACES region at both two end states. Now, ACES was published kind of 2 years ago, and recently my work has been focused on how to even like further optimize it with the alchemical enhancer sampling with optimized phase space overlap. Now this picture of me was also optimized a little bit. So as I described, ACES, the method is designed perfectly for sampling some kind of conformational energy barriers or those high energy barrier like, events, conformational events in your simulations. Now here is a case study that the application to the ring flipping events in SARS-CoV-2 main protease inhibitors. This graph is a perturbation map, a dense perturbation map between like 4 congeneric ligands labeled as 18, 19, 20, and 21. These 4 ligands, they share the same molecular scaffold, and they only differ in this kind of azo group. So one thing is that the placement of these 1 nitrogen atoms on the ring, and another thing is the kind of the replacement of these hydrogen atoms replaced by a kind of methyl group. So all these 4 ligands should bind inside the binding pocket. But if we kind of introduce this kind of methyl group, clearly the hydrogen bond will be gone. So as such, like steric hindrance would either push the ligand out of the pocket a little bit, or it has to kind of adjust its position and fit it inside the pocket. So in this case, likely this whole the azo ring should kind of flip according to this kind of single rotatable bonds. And here we tried we're going to compare like different methods, and especially if we're using the maximum common substructure algorithms to define or to minimize the perturbation region, it will give the soft core region as the hydrogen atoms to the kind of CH3 group. But in our AC simulation, we're going to include this whole azo ring into the soft core. We want to enhance the sample, the conformation of this part. And here I'm going to show some result. So we just focus on this kind of single rotatable bonds. And as we know, the conventional or the plain MD simulations would depend heavily on your initial configurations. And this holds true for all 4 ligands. Now, in this first column, we show the torsion distribution using the plain MD simulations. And if we kind of analyze the whole torsion distribution across the whole trajectory, and it is clearly that if the MD simulation would just stay where it is when you started. So if you started from the kind of the red torsion, you would just stay in red for the majority of the trajectories. If you're starting from the black torsion, it would just stay in black. But on the contrary, ACIS simulation could produce a consistent, reliable, and converged conformational distributions for these ring flipping events. So no matter where you started from red, you started from black, you will always get a very similar converged torsion distribution for all 4 ligands. And further, we compare different protocols for the comparing the using ACIS and some other. So for this column, I'm showing the no RE, which means no replica exchange, but the enhanced sample region was still that azo ring. Now, as we can see, we compare the whole all the alchemical transformations. There are kind of the dense graph. So for each ligand, there are kind of 3 edges involves it, and the arrow, the mean absolute arrow of the torsion distribution for each ligand would be over 0.3. And now the MCSE means that when we identify the soft core regions using the MCS algorithm, but with the replica exchange, so the mean arrow decreases a little bit. Now, furthermore, for the ACIS simulations, it actually produces the least amount of error, so that ACIS could improve the sampling and increases the accuracy of the conformational distributions. Now, all this sounds very good, but it actually comes with a price. Why is that? All the simulations was running with 21 lambda windows for 5 nanoseconds. Is there a way to kind of save some computational resources? Now, the idea here is to use the ACIS with the optimized phase space overlap lambda scheduling. The idea here is we will first run a very short burning simulation with a large number of lambda windows. Now, in this particular case, I was using 21 lambda windows. The burning simulation was typically around several hundred picosecond. Now, this is 500 picosecond. Now, based on this burning simulation, we would come up with a whole new set of lambda windows. Now, in this case, I come up with kind of 12 lambda windows in total and run the full production runs till the end. Compare this burning simulation with actual production, the overhead is only about 5%, but the final free energy result is still within the comparable convergence. Here's how we do it, how we optimize it. Here, I'm showing the kind of the 2D map of different indices we use to optimize such schedule. Now, each row corresponds to one different alchemical transformation. And in the first column, I'm showing the kind of the heat map for the phase space overlap between 2 arbitrary lambda windows. So along this kind of diagonal direction, it means kind of the overlap of each lambda window with itself. So it should always be 1. But in these off-diagonal directions, so as the 2 lambda windows become more distant, become further away, the overlap should have decayed to 0 very quickly. And then we would, given a kind of a total number of your new set of lambda windows, we try to put insert this new lambda windows positions along this diagonal. That's the kind of the small black dot here. That this new set of lambda windows will try to equalize and maximize the phase space overlap for all the lambda intervals. We actually tried some kind of other indices. The second is the callback labor divergence for the potential energy distribution for each lambda window. And the third is optimized replica exchange acceptance ratio. And among them, it seems like that the optimized acceptance ratio will give you is more persistent to the noise that is generated by two distant lambda windows. But in general, all these kind of three indices will give you a very similar, basically no significant difference in the new set of lambda windows. And here we're going to analyze our new set of simulations. So here I'm showing kind of the two chemical transformation examples. Now that's the two kind of columns. And then in each row, I'm showing the different schedules for the lambda windows. And each curve corresponds to either a phase space overlap or replicate exchange acceptance ratio. So first thing first, that we see that no matter which transformation you are in or which kind of scheduling you are using, the phase space overlap is always highly correlated with the acceptance ratio. So whenever you have a higher overlap, it is the higher the chance that the exchange between two replicas going to be accepted. And now all these simulations were using a total of 12 lambda windows. And if we compare with this kind of a linear spaced, this GL stands for a Gaussian quadrature variant called Gauss-Lobato, which reaches exact lambda equal to 0 and 1. Now, these predefined schedules, they all have a severe bottleneck in the replica exchange chain. Like sometimes you will get a kind of acceptance ratio even lower than 0.1. Well, compared to our optimized schedule, first, the overlap and the acceptance ratio, they are uniform and maximized across the whole lambda windows. And also, this kind of horizontal dotted green line is a prediction from the burning for the optimized for the phase space overlap. And actually, our production agrees it with it very well. And it is largely due to that the situation that the optimized schedule will put more lambda windows towards the middle, where more sampling effort is needed. So then we look at some statistics about how the efficiency of replica exchange was improved. So there are two numbers. One is the number of single passes, the number of occurrence of single pass, and the number of round trips. So single pass is defined as one replica travel from lambda equal to 0 and go to 1, or from 1 to 0. And the round trips is defined as any replica starts from its original position and it reach to end state at least once, respectively, and go back to its original position. In this case, our optimized schedule, you can see that it increases obviously for both the single pass and round trips, meaning that the efficiency of replica exchange is kind of improved a lot. You need less exchange attempts to traverse the whole lambda ladder, and there will be more visits to each state by more replicas. And I want to make a kind of advertisement that here, all these lambda scheduling and analysis tools they are already available in the FE toolkit module distributed with Amber Tools 25, which was just officially released last week, I guess. Amber Tools 25 is free to use. You can just try it for any projects. And some ongoing work that I've been doing is to targeting the MIF system using the hybrid approach of the RBFE plus CBFE. So this all these ligands from the published work from Jorgensen's group. For the red edges, I was using the CBFE, while for the kind of dense graph, I was using the RBFE calculations. Here's a very preliminary result. So this project is to really mimic the real drug discovery project. This started from one ligand, try to hop to scaffold hopping to another kind of set, then optimize that scaffold. Now this the free energy result is very preliminary, but I'm quite happy with it. So most of the simulations falls within a 1 kcal/mol error range. Some of them a little bit higher, and I'm going to kind of use this optimized schedule to further improve the simulations. And next, I will really briefly discuss about some models for the machine learning potentials developed within our group in another branch. So we're using this kind of, we developed this quantum deep potential interaction model, and Darren named it QDPi. We all seem to like it. So we are using this kind of indirect bookending approach, actually, So we will correct a simulations at 2 n states respectively from the level to a QM level. So QT-Pi1 was published 2 years ago. The QM delta machine learning potential was based on like DFTB3 and trained against omega B97X. And recently, like last month, the QT-Pi model, the QMM delta machine learning potential, was published. It was based on the GFN2 XTB and trained against a higher level of theory. And some like really quick result for the QT-Pi1, it is accurate for polymers and protonation energies both. So we compare with different models or the different theory on different kind of data set, and it all turns out very good. And for the protonation energy, it almost kind of agrees like a apple to apple agreement. And for another set of the ages, which includes natural and synthetic nucleic acids, where hydrogen bonding pairs will be kind of formed out, and also each kind of nucleic acid will have the different polymers. QT-Pi is also accurate for this hydrogen bonding predictions and corrections, and also accurate for the ages polymerizations. And QT-Pi upgrades the robustness and the quantitative accuracy level. Like furthermore, it is not only a model, it also comes with the QT-Pi2 data set, which kind of extracts data from various large data set with the active learning filter to maximize the broad and reduce the redundancy in the chemical space. Now, all this kind of tools, they are already in the Ember free energy tools for the QMMM and the machine learning potentials. You can just try it out. And again, FE Toolkit is now available in the Ember 225 and our own GitLab repository. If your project happen to want to scan the free energy surface, the n-dimensional free energy surface, or if you want to do the alchemical free energy network using analysis using MBAR or TI at the same time, or you want to use the lambda optimized lambda scheduling, you are free to try it out. Again, FE Toolkit is arbitrary. It does not really know your underlying MD engines. It only cares about your data you feed it to it. If you are using kind of any other program to run alchemical free energy simulations, FE Toolkit should be able to do it. And the application notice was just accepted to the JCIM, I guess, yesterday. So finally, I want to express my things there. Thanks to my advisor, Darren, although he's not here, but I'm really grateful for these opportunities. And also, I want to thank my collaborators, our former lab mates, Shi Zhang and Abir. They are also here. They are now at Tandem AI. Shi Zhang has a poster today, and Abir has a talk tomorrow. And I want to thank the federal funding until when I still can. So finally, I want to make this one last advertisement for myself. So I'm about to graduate within a few months, and this is like the pre-defense a little bit. If anyone is open to hire, I'm open to be hired. Okay, and one more last thing is if you have any problems or if you want to chat, want to connect, feel free to send me an email. This is my email. And if you have any questions for Darren, you can shoot him an email directly, which will likely be forwarded to me. So yeah, I'm happy to take any questions. Thank you very much for your attention.
Thank you, Shi.
Yep.
We have time for a couple of questions.
Okay.
Any questions?
Yep.
There you go.
Okay. What selection? The restraints for the ABFE. How do we choose it? Yes, we have some like automated scripts to choose the burst restraint, especially if we want to do that. So we could run each end state. You can run plain MD simulations or the self-ACIS, self-to-self transformation. You just for the simple purpose of enhanced sampling, and then analyze the trajectory and get the average structure, get some like average either distance or the angle or the torsion distribution. The torsion angles. then we get just average structure, and then set that as the kind of harmonic restraint to hold the ligand inside the binding pocket when we turn it to dummy state. It will be a heavy atom. So right now for the protein side, it will be the backbone C alpha. And on the ligand side, we will just go for try to expand across the whole ligand and find the first will be the carbon and then will be the nitrogen. Ideally on the scaffold, not really on the terminal like functional group. And also there are kind of different effort other than the Boresh restraint, those specific kind of bond angles, like such as the RMSD restraint that we've been trying to doing it, and hopefully kind of get some like new result sooner. Yeah.
We have another question.
Well, I guess it's the embedding, because well, I'm not the really the expert in the machine learning here, so we have a really brief case. I think we should have the embedding, I guess, here. The down right corner. I'm not really sure about that question. I'm sorry.
Let's thank Shi one more time.